In this next example, we'll keep you on your toes a bit by changing the terminology or the symbols we use. In this case, we're going to call this graph f prime of x, which is what it has been all along when we're doing antiderivatives, but that means the graph we're trying to build is the original f of x graph. So here we're given the derivative and we're trying to find the original. That's exactly the same as being given a function and finding the antiderivative. All right. So if this is our derivative graph and we're trying to build the original, then one of the things we can use as landmarks, of course, are critical points. And the critical points of f are the points where f prime of x equals 0 or is undefined. Now you just have to be careful here. This is a graph of f prime. It's not the graph of f. So literally we are looking for places on this graph where the values are 0. There's a value of 0, a value of 0, and a value of 0. The temptation at this stage is to look, oh, cusps. Cusps are undefined derivative. Hold on. This is not the original graph. We're not looking for cusps of this. We're looking for 0 values or undefined values in the derivative graph. The function is perfectly well defined everywhere. There's no asymptotes, there's no gaps, but it does have 3 0 values at x equals 1, 3, and 5. So the only critical points are x equals 1, 3, and 5 of the original function that this is the derivative of. So just be careful which graph you're looking at when you try to make an analysis. Let's work on a sketch then. We've got a few different areas we can compute pretty easily here. This whole height is 2 and this is 1. So this area is, again, it's an area in quotes, it's an integral value is -1. This area would be 2. This area would be -2. And this last area here would be 1. We also had some other information about the sketch. Oh, wait, we have one more piece of information on the last page. F of 0 equals 1. So we're given the derivative, we're looking for the original function, and it starts at 1. Let's make that 1 there. Okay. If that's the case, then, actually let's make 1 just a little bit lower. I think we're going to need some room here. What's the translation? Again, we have y values on this graph translate to slopes on the original. So this is f prime of x, which if we integrated it would give us f of x, or if we differentiated it would get us back to f prime. And integral areas translate to changes in this function, whatever we're calling it, changes in that function's value. With that, actually, it becomes pretty straightforward to build the sketch. So the area here is -1, or the integral value is -1, and so we're going to go down by 1. From here to here, the function is going to change by -1. Then it's going to go up by 2. Then it's going to go up by 2 by the time it hits x equals 3. That lines up there. This next area from 3 to 5 has a -2 integral value, so this function is going to go down by 2, and then last but not least, up by 1. What are the slope values? At 1, 3, and 5, we have critical points, so they're 0 slope values. Oh right, that's where this derivative equals 0. Next, we can connect the dots using our slope ideas. The slope is initially -2, and then it goes down to 0. And then it goes up. And it's actually it's going to be hard to see that this transition here is as sharp as it is. We're going to get something that looks pretty much like this. Very much like a smoothed out version. And that's a common property of integration, is that it smooths out rough edges. And this would be the graph of our original function. We have all the details from the areas and the y values translating to slopes. The largest y value is in the middle, the steepest slope is in the middle, so we get some kind of, we get a point of inflection at that point. But the basic shape of the graph is dictated mostly most easily by computing these areas and using that as the change in the height of the function as we move from left to right.